So based on our last lecture, we now have a tool, this theorem here, for determining when a graph has an Eulerian circuit. And that's awesome. It's a great tool to have in a toolbox. What I'd also like to have is a tool that tells me when a graph does not have one. And remember, you have to be careful about these things. When we're dealing with logical statements, trying to just infer or use your intuition to come up with results is a risky business. Better if you follow the rules. Right, so what I'm going to do here is I'm going to actually take this statement that we also talked about in the last lecture, and I'm going to use this to derive a statement that I can use to answer that question. When does the graph not have this kind of circuit? We're going to use some of the logical procedures we talked about earlier in the class. If you haven't watched those lectures, that's fine. You can just jump ahead to the end of this slide and just look at the final result. So what I'm going to do is I'm going to look at the contrapositive of this statement. Because remember, if a conditional statement is valid, then its contrapositive is also valid. So the contrapositive is going to be this. I have flipped the if and then parts, the antecedent and the consequent. You want to be technical. And I've negated both of them. And I've been very brute force about the if part. I just glued not in front of that whole statement because we're going to be a little careful about how we simplify it. So the way I'm going to do that is I'm going to apply De Morgan's law. Remember De Morgan's law that says not P and Q is equivalent to not P or not Q. So that's what I'm going to do next. I'm going to replace that parentheses part with not connected or not. And again, I'm being very inelegant at this point. I've just put not and that last part in parentheses because that last part we got to be careful about. That is a universal statement. It's a statement about every vertex. The negation of a universal statement, that's an existential statement. Right? So the negation of that part will be there is at least one vertex that is not even, in other words, at least one vertex that's odd. And that's the statement that I was looking for. Notice the then part here. The then part is the graph does not have an Eulerian circuit. And that's what I was looking for. I was looking for a set of conditions that I can evaluate to determine if a circuit does not exist. If we kind of wipe out all the middle parts here, right, that these two statements are going to be really my main tools, right, for answering questions about the existence of this kind of circuit. Okay, so let's look at some examples. This is finally our Konigsberg Bridge problem. We're finally in a position to answer this. Does the bridges of Konigsberg have an Euler circuit? And the answer here you can see pretty quickly is no. If you just look at V1, its degree is 3. There are 3 edges touching it. 3 is odd. So by our new theorem that we just talked about here, because the graph has at least one odd vertex, it does not have an Euler circuit. So the ultimate question to the ultimate answer to the people of Konigsberg question is no, you can't do what you were looking to do with your bridges. All right, so how about this one? Does this graph have an Euler circuit? Well, the answer to this one is also no. This graph is not connected. Vertex V1 up there in the middle of that upper left-hand circle isn't connected to any of the other vertices. So again, this is hopefully that's kind of intuitively obvious that there's no circuit here because there's no way to get to V1. But again, our theorem does cover this case. The graph is not connected, therefore such a circuit doesn't exist. And I got one more here, and this is again it's another kind of weird case, but it's instructive to look. It's instructive to look at weird cases because our theorem has to apply to them. So here our graph is connected, and the degree of vertex V is 2. It's even. So by the theorem from, actually this is the one from the last lecture, yes, this graph should have an Euler circuit, and clearly it does. You just go once around the loop, and you've started and ended at the same place, and covered every edge. Okay, so now that we have a way to decide whether or not these circuits exist, the next obvious question to ask is, well, if a circuit does exist, how can I find it? And sometimes you can just figure it out, especially with smaller graphs. You can just kind of look and try a few things in your head, and you're, okay, yeah, I got the answer. Sometimes with more complex graphs, it's not quite as obvious. Well, fortunately, we have an algorithm or a procedure that we can follow to answer this question. And the way this works is I'm going to find a bunch of kind of sub-circuits within the larger graph, and then I'm going to glue them together in such a way that I get a circuit that covers the whole graph. All right, so here's how this works. You need to start by picking a starting point, and the point you pick doesn't matter. You're going to get the result you're looking for either way. I'm going to pick vertex V2 to start with. So what you do from here is you plot out a circuit that starts and ends at V2. Now, such a circuit has to exist because we know, and I kind of glossed over this, but if you look at the degrees of all these vertices, they're all even. So there is an Euler circuit here. And because there's an Euler circuit, there has to be a path between a circuit that connects every point to itself. So I'm going to plot out such a circuit here. Right? I'm going to go 5, 6, 7, 8, 9, 4, and 2. Now, yes, there are other options I could have chosen. I try to go big when I'm doing this because the bigger mini circuits you can find, the fewer of them you're going to have to find. All right, but if you went smaller, that's absolutely fine. You still get a good answer. So what I'm going to do next is I'm going to remove. Oh, excuse me. What I'm going to do next, I'm going to note the circuit that I came up with here. Right? We go 2, 5, 6, 7, 8, 9, 4, and then we finally get back to 2. Right? Now I'm going to remove all of the edges that are in my mini circuit, and I'm going to remove vertex 6 and 7. I'm going to remove any vertices that were orphaned, if you will, as a result of my taking away those edges. Now I'm going to do it again. I'm going to pick a new starting point, and once again, doesn't matter. Pick any point you like. I'm going to go back to V2 because it worked well for me the last time. And I'm going to plot out another mini circuit from V2 around to itself. Okay, I'm going to write that one down. And then again, I'm going to erase all of those edges and all of the orphaned vertices. All right, now we made it to the end of our process here, right? We pick any starting point you like. We're going to get one more mini circuit. I started at 4, went from 4 around to 5 to 8, and back to 4. Okay, let's go back to the original. There's the original graph again. So here's how I'm going to assemble these 3 mini circuits into one big circuit that covers the entire graph. I'm going to start with circuit C1. Now notice that C1 ends at vertex 2 and C2 starts at vertex 2. So I'm going to take this C2 circuit and just glue it onto the end. Okay, almost there. Now look at C3. Notice how C3 starts and ends at V4. And if you look closely at my circuit C here, it's got V4 in it already. So what I'm going to do is I'm going to insert this C3 circuit, that's going to be 5, 8, and 4, in that gap. So you see what I did here? If you're following the circuit along, we go 2, 5, 6, 7, 8, 9, 4. Then we take a diversion. We go 5, 8, back to 4, and then we pick back up on the original larger circuit. Right, so that's kind of what I mean by where we take the mini circuits and insert them into each other to get our final result. Okay, so now we've added some great new tools to our toolbox, right, related to these Euler circuits. So what we're going to do in the next couple of lectures is we're going to say, well, suppose we loosen up our requirements a little bit. Suppose we remove the requirement that this path we're taking has to start and stop at the same point. Without that requirement, is it possible to plot out a path that covers every edge exactly once? Like, can we still meet that other requirement? The result of that is what's called an Euler trail. And as you'll see in the next couple of lectures, there's a very similar set of rules that we can use to determine whether or not one of those exists. So if you like this lecture, please don't forget to click on the like button down below. And there's some additional links here to take you to that next lecture or to subscribe if you'd like to do that as well.